Chen, talk about physical space decimation, constrained large eddy simulation.
I would like to thank the organizer to invite me because I like this meeting so much. So within 1 month, I flew from China to here twice. So I call for competition, someone can beat me. And that's first. Second one, I really also thank the organizer putting me the speaker after this very nice lecture. Therefore, I essentially don't need to do any introduction. So let's see if this is going to work. Okay. In the last couple years, I was thinking about a problem. Listening all these nice talks, they have wonderful understanding fundamental physics fluid turbulence. But we know that in the two groups, one group doing engineering simulation, another group of people they are doing fundamental physics. The community is, to a certain degree, they're separate. So what I'm asking a question: can we really directly use fundamental physics to learn from our research on fundamental turbulence for model and simulation? By the fundamental physics, I meant, for example, conservations of energy and helicity. For 3 dimensions, these are 2 implicit conservation quantities, and also like energy fluxes and scalar fluxes in inertial range, even intermittent exponents. Can we use this? For channel flows, we know that in a mean flow will satisfy certain Reynolds stress, for example, for separation. So how we put these 2 together? Okay, that's a question I'm asking myself. So that we will be able to do something. I think is try to do minimum work to see if it's work. So we so-called constraint variation, or we essentially learn from this renormalization group analysis in free space. We move to the physical space. That's what I'm trying to say. So let me remind you what we have done. Look at Krachner, the paper. In early paper, look at the decimation theory. He wrote a very nice long paper in decimation theory in 1975. He and I, we did a little work on that in 89. So let's think about the free modes. So xi now is not a position; it's a free modes. So you can write down as an equation in free space. Therefore, you see the S essentially separate. Suppose you have n modes. Okay, n is a total free modes. So think about S is a mode you consider internal modes, larger scale, whatever, in the inertial cutoff. But therefore, essentially, Qi is a mode essentially not included in the inside mode. So it means small scales. That's very typical. We do this kind of thing for the normalization group. And this Yan Zhou is here. He has done this many years. And also CJAR and a lot of other Harvey, CJAR, and so on and so forth. They do this kind of thing. Okay. But in the decimation idea, essentially, when you want to work out the statistics, you want to try to constrain these like Brownian motion terms in decimation theory. So you look at, essentially, we can use the constraint. Essentially, this is a small scales, okay? But you also can work out identical terms. The coefficient which is decided by this, the flatness is about same, but essentially a coefficient over there. So essentially, if you want to solve this Q to put it back in the equation for finite size S solution, you try to constrain them. So what I'm trying to say, you find a mean quantity is equal to this Qi, Q star, which is inside mode, internal mode, not a small scale. Also, you will constrain the second order. This is like a flatness. Okay. Then also you can constrain intermittent. That was a paper we did in 1989. And you also can write down that essentially two time correlation, which essentially the 2 time with Q and Xj free modes. This essentially is the energy flux constraint. Only use this equation and this one constraint, you can reduce to that direct interaction approximation. That is in paper in 1975. So all others theory essentially doing the same thing, try to essentially put a constraint on this term. That has been done in free space. The question, can we do the same thing in physical space? To learn this, can we use it? So let's now jump to the physical space approach. The physical space approach we all know is the so-called large eddy simulation. Okay. Now you look at large eddy simulation, you do that as a velocity field in physical space, a field. Now you look at the field equation, then you look at a very similar, okay, this is essentially tutor, like a Hudong, this yesterday we have this problem. So look at these box essentially like tutor over there. Now you see that essentially you also get Fi. The Fi is equal to derivative of this term and associated with subgrid stress. So what I'm trying to say, if you look at free space and physical space, the look is very similar. Okay? So essentially you have the cutoff here and so on and so forth. But in fact, in the large eddy simulation, we never really take advantage of so-called constraints. Let me tell you what people have done so far. And first, let's look at how important the term that tau I just subgrid stress. The subgrid stress is associated with the so-called local energy flux, which plays a key role. If you look at energy, U tilde squared, there's a subgrid stress over there. So essentially, this is a very important term, essentially for your energy transfer between small scale and larger scale. You can see this. This is coming from larger scale. This comes from small scale. The interaction of them. Now, let's think about how people do the subgrid large eddy simulation. So what do people do? First, they take very simple models, the Szymanski model. They assume this subgrid stress is proportional to the strength rate tensor. One thing you can do is assume CS is constant. That's Szymanski model. Then other people say, okay, let's do dynamic model. So what I'm going to do, I'm going to take the constraints to put into dynamic Szymanski model. So what dynamic Szymanski model is say? Let's make assumption of this tau ij in the delta scale. Now let's apply to the 2 delta scale, the smaller k and larger scale. Essentially, genomic equality allow you to derive this AOIG term exactly based on 2 delta statistics. If you do larger simulation up to this point, then all the quantity inside of this is known. Therefore, this quantity can be calculated exactly based on known quantity. Okay? Therefore, you essentially also can cook up AOIG because AOIG, this term and this term. They are all modeled. So essentially, you can make a difference of this known quantity and a model quantity make error. So if you want to calculate these C coefficients, so-called dynamically, you make difference of squared, do the mean square, then you do delta epsilon delta C to determine this coefficient locally. That's the so-called dynamic process of the large eddy simulation. Now you can also do this not only for one coefficient. You can do many terms. Okay, you can add a symmetrical part, anti-symmetrical part in combination, and a higher order, and so on and so forth. So now if you look at this, I'm telling you here, you're going to do the so-called mixed model. There are 3 groups. One is one so-called Szymanski model, second one so-called similarity model, and third one called nonlinear model. You can do add all them together by coefficient C1, C2, and C3. Then you do derivative of that. You make error function, do derivative. Then make it 0, then solve 2 by 2 or 3 by 3 matrix. That is called dynamic procedure. Okay? So my question is, how can we add our physical understanding to this procedure? That's what I'm going to do. So first thing we tried in the physical space, we call the constraint subgrid stress model. So let's try two terms. So you make the tau ij model to be 2 terms. One is based on Szymanski model, and second one based on similarity. In the original approach, you just do arrow function, do derivative on C1 and C2, make it 0, you solve it. But turn out that it's not going to work. Because we all know that for the people working on the large eddy simulation, they know that. If you do that, this kind of results will not give you the right dissipation. Because why? Because you add this similarity term. You increase the correlation function, but you don't, I will show you later, you will not do very good in the dissipation. That's because the model itself does not incorporate the energy flux in your system. So what I'm trying to say, why not during this variation principle process, let's do constraint variation. Instead to do variation, you do partial epsilon partial C1, partial epsilon partial C2 equal to 0, solve the equation. Why not we do variation principle, then do the constraint variation? So what's the constraint about? I say if there is an inertial range, then the fluxes across the inertial range at delta scale and 2 delta scale, it's almost the same, equal. If there's infinite Reynolds number, that must be exactly the same. Okay, if they are not the same, in fact, I've done this. It can also be done by the energy fluxes through the scale alpha. So you can do 2 delta, 1 delta, you also can do alpha. Another comment I want to make, if the system does not have a good inertial range scaling. In fact, for all the data we have done, we don't use this exactly. We use extensile similarity version of it. The work is much better. So what I'm trying to say that these statistical mechanics we learn through mechanics for turbulence, in fact, it can be used. Can be used for this kind of system. Okay. Now, so if you have energy and helicity fluxes, now we can add one more term here. 1, 2, 3 terms. Now you can add that this Rij is anti-symmetry of your stress rate tensor. Okay, it's your strain tensor. So you put 2 constraints. Now when you do variation principle, you put 2 constraints. One is energy flux constant, and another one is helicity flux constant. So the constant, how many constants you can put into it? As long as you have n coefficient over there, you can put n minus 1 coefficients, because that 1 coefficient can be determined by your variation. So that's essentially the idea over here. Okay? And also, we are trying now. And what happens if we want to do intermittent? Essentially, you can look at flux square term at delta scale and 2 delta scale. Then you use scaling exponent, you can work out. The alpha is essentially it's alpha delta, the bigger size, alpha bigger than 1. Therefore, essentially you get 2 minus psi 6, which is the velocity increment, the scaling exponents for 6th order. You also can do this for beta, then you have a coefficient over there, and so on and so forth. So what I'm trying to say, that what we learn from the statistical mechanics of fluid turbulence can maybe able to apply directly to the larger simulation. That's the basic idea. Let me just show you some results. Okay, first thing we tried, let's do the isotropic turbulence. So that's what we did a priority test. The priority test essentially tell you that there are 2 things here. One is energy flux. Let's see, it's energy flux 0.092. If you do Szymanowski model, it's bad. All these bad, non-constrained, non-constrained. If you constrained, you got very consistent, much better than non-constrained. Also, if you do this Szymanowski correlation function, you see it's very bad. Now, if you constrain and non-constrained, if you use similarity model, all these constrained model, the correlation function is very much close to these so-called similarity models. So what the constraint essentially give you, you catch both sides. You have a correlation function very well, your energy flux very well. That's what you see here. Without constraint, you cannot catch both of them. Essentially, the reason essentially because you put the constraints in your variation process. And also we look at an posterior test. You can see that this is a C means a constrained dynamic mixed similarity model. It's almost give you the best. But if you only do dynamic mixed similarity model, you don't really get the energy flux as well. So it's the worst in this one. On the other hand, if you look at the PDF for energy fluxes, now the Szymanowski model essentially doing quite well because it's dissipative. Then turn out you have a cutoff. You don't get a negative energy flux at all. Whereas this constrained one, a dynamic mixed model, you almost give you the same results. So what I'm trying to say, you catch both sides through these constraints. And this probably you can see also from PDF. Now it's matched quite well for the tau 1 to the PDF. This is dynamic. A Szymanowski model based will not give you this kind of thing, and so on and so forth. And we also look at essentially force the case for the steady state constrained dynamic mixed model. It's at least better than without constraints. For the dissipation model, it's turned out for any spectrum itself is not bad, but correlation is not good, and so on and so forth. Another one you can look at, intermittent, for fourth order quantity. And the moment it appears to be with the constraint you most close in the inertial range. For this one, I did not put in the fourth order constraint yet. I just look at second order. Turn out it's not bad. You can see this kind of, if you look at this essentially coming from that, let's see, dynamics model. This one come from dynamic Stravinsky model. Both of them without constraints. With the constraint, you get quite good results. Let me just move on. And we also did this with non-helical turbulence, and we have done a helical turbulence as well. Let me see. Okay, this probably, and this is the decay one. The decay one is very sensitive. What we have done is this is somehow switched, and probably just let us guess what's the inertial condition, But let me tell you, the inertial condition is a compact spectrum. Let it decay. So it's a k⁴ exponential. It's a compact. I don't know why it's this way, and because maybe when I edited something, they were switched. And but let me tell you, I will run out of time very soon. But let me tell you, essentially, you can see that this is the dynamic mix model. You don't catch the energy flux quite well, but there's this constrained dynamic. Oh, what's this? Constraint dynamics give you order as consistent with the dynamic Stravinsky model. So what I'm trying to say, dynamic Stravinsky model essentially try to catch this dissipation. It turned out quite well. Similarly, type of the model give you all the correlation and so on and so forth. If you do constraint, you get both of them. Okay, this is for helical turbulence, and we have done mean kinetic energy and mean helicity. Okay. Let me spend 5 minutes because I start late. Okay, what I'm trying to tell you, this kind of idea also can be extended, not only for isotropic turbulence, can also extend to constrain at Reynolds stress. So what I have done this with channel flow. The channel flow that now is very popular. People talking about hybrid with RANS and AOES. The idea is that you do the RANS inside of your inner layer. You do outer layer to do so-called large Eddy simulation. So this is the most popular way to do it. Is so-called that detached Eddy simulation. Okay, but we know that detached Eddy simulation has a problem. Let me tell you the why. So this is the results. You got it. Okay, detached Eddy simulation. This is the dashed line. This is log layer. Okay. These all lines, you can see that essentially you don't really get this log layer very well. If you use the detached Eddy simulation, you do RANS inside and rapid transition to large Eddy simulation. That's a detached simulation by Splar and other people. The problem is, let me tell you the reason. The problem is, when you do the RANS inside of your channel, near the wall, essentially you are doing a RANS. Therefore, there's no small scales. Whereas outside, if it's AOES, you have a small scale. So you need a certain space to allow your small scale to grow. Therefore, that's the problem. Lack of small scale fluctuation in the RANS area is the main shortcoming of the hybrid RANS and AOES method. Now, let me tell you what do we do. I'm not going to say this. That's forcing scheme because time constraint. Okay, what do we do here? For channel flow. So what we do here is the following. We do the whole domain with large Eddy simulation. But we constrain in the inner layer, constrain the Reynolds stress. We can constrain Reynolds. As I told you, you can constrain something. Now, when I do large Eddy simulation, without constraint, you will not get a good result. So what I'm trying to say, when I do the large Eddy simulation, I do the constraints in the inner layer, which essentially is solution equal to the Splar and other detached Eddy simulation. Essentially look like I do the detached Eddy simulation because inner layer is a RANS with solution, outer layer is the large Eddy simulation. But in fact, it's not because I do whole domain is large Eddy simulation. Therefore, small scale all generated already. I only constrain the inner layer, the Reynolds stress equals to SA model. or algebraic model, or any model you provide. That is the idea. I'm not going to tell you, because time constraints, I'm not going to tell you all the how I did it. Let me tell you, there's some mathematics going through it, but essentially it's exact results. It's accurate because it's based on the connection between that Reynolds stress and large Eddy simulation as a subgrid stress. You can work out mathematically. Okay, the idea here essentially you have to constrain something which did not think it through before. We are now be able to do it. Let me just show you some results. Okay, for channel flow. So this is the result. We did a simulation for channel for R tau equal 180 to 590. So this is you look at the coefficient here change as a Reynolds number. That's the standard. Now this is essentially is a result for our result to compare with the log law. Okay, and then let's compare with mean velocity profile for Reynolds stress constrained large Eddy simulation and non-constrained AOES using dynamic Stravinsky model and DES detached Eddy simulation. This is a line essentially coming from the log law, common law, and also our simulation. These two lines from others. So even for mean flow without a constraint using detached Eddy simulation is not going to work. We have done 1,000. We have done 1,500. We have done 2,000. Then let's look at the drag coefficients, skin friction coefficients. We compare with the Dean's experimental data. This is our results, arrow, compare with the Dean's result within kind of 3 or 4%. Whereas the detached Eddy simulation, you got essentially 15%, and AOES with the dynamic Stravinsky model give you 15 or even higher, 20%. During this procedure, our mesh size is very close-grained. It's really, we use the same mesh size as detached Eddy simulation. For this simulation, we always keep the grid like 64, 32, 64 so all the way. So the very close-grained, we still be able to calculate the frictions. This I'm not going to talk about where we are going to match it. But we also look at the Reynolds stress and other quantities seem like it's quite well matched with the DNS at the moment. So I'm not going to get detailed and structures and so on and so forth. The one thing, the detached Eddy simulation, because there are no small scales, if you look at all these so-called streaming-wise functions, you only got a larger scale. You don't see a small scale by nature because there are no fluctuation. Now we add small scales. This is a dynamic Stravinsky model. You see small scales because it's larger simulation. Also with us, we also see the small scales. Okay. I should leave 5 minutes for discussion. We are working on all these complex flows and with separation now. And essentially this one we are getting quite close now to compare with a detached Eddy simulation for spherical particles, cylindrical geometry, and so on and so forth. And that essentially done now. It turned out quite reasonable and with the separation and so on and so forth. So let me I put over there a conclusion. I'm not going to read this, but last one I like to remind you. One may impose different constraints to capture underlying physics for different flow phenomena, such as intermittent. We write down, we did not get done yet, which is important for combustion and magnetic. Also, we can do magnetic helicity, which we already done. We have done for helicity, which could play an important role for magnetohydrodynamic turbulence. And we also think about put the compressibility effect on these kind of model. Okay, thank you.
Question, please?
What do you do with separations? I mean, which kind of observable are you going to constrain in the case?
The separation is not really done by the larger simulation. Separation essentially there's a good model like SA model or K omega model or so on and so forth. So even you can add a compressibility and so on and so forth. So we essentially what we are proposing, say, let's take this Rance model, then we add it with AOES model. But for them, if you don't have constraint, you have abrupt transition. Will not give you a good result. So if we do AOES following this kind of idea, we may be able to extend your accuracy and so on and so forth. So we are not going to develop new the range model for separation. We just try to say we match the scheme using the constraint will give you better results.
I have a generic question. How well do these models, these reduced models, do in the Lagrangian domain, so in the temporal range?
Okay, very good question. We have done this. We have done this for the larger estimate. We have done SA model. We have done different algebraic model. We have done this other models. We also have done this with the time, with Lagrange method proposed by Charles Manuel, and also the without Lagrange, just time relaxation method. We have done it. There's for channel flow. There's essential Lagrange is essentially, in fact, the same. It's even better for other systems. So depending on you have average direction or not, for without average direction, you have to use this Lagrange model or time model. We have done it.
But you did your modeling with a mixed model. But if you just keep similarity part, if you impose constraints, will you be able to make it workable? Model which normally is not workable.
That's a very good question. As I say, if you have n coefficients, maximum you can impose n minus 1. I still personally believe the genomic equality is very important. We did not try yet, but we can try. Just ignore genomic equality, try to constrain flex. It's going to work or not. We always keep the genomic equality as our basis. Then we add more constraint.